Everyone, welcome to the last but very much not least talk for today. It's my honor to introduce Avi Wigderson from the Institute of Advanced Study, talking about the asymptotic spectra, which is a joint work with Joran Zoida.
Okay, hi. Yeah, it's great to be in person in Berkeley. I'm sorry for all the people who couldn't come. It's perfect weather and a real live conference. Yeah, what I'm going to tell you about is not new in any means. It's a theory that was developed by Volker Strassen in the late 70s and the 80s on asymptotic spectra of tensors and beyond. I'll explain it. The reason we spend a lot of time actually on writing a modern survey of this theory is that since his work was focused on tensors, and in particular trying to understand matrix multiplication, there have been many other applications or settings in which his theory applies, and I want to at least mention them. Anyway, the survey has many more, and in general has much more information than the highlights I'll give you in this 50-minute talk. But anyway, those who are interested in more, there's almost a final draft on the website of Yaron. I still didn't put it on mine, but anyway, we'll be there, and we hopefully are going to post it in a couple of weeks. So it's a beautiful theory, and I want just to give you, some main insights from it, and tell you in particular why it's about optimization and where our symmetry is there. But there's a lot more beyond that. So this is more or less the plan of the talk. I want to start by in general motivating this framework, which comes from just understanding asymptotic costs and amortization. Then I'll talk specifically about the matrix multiplication problem, its complexity, and tensors and tensor rank. I'll then generalize it to the setting in which Strassen presents his theory, which is a setting of pre-ordered semi-rings. I'll explain what this is, and I'll just tell you about one setting very different than tensors. It's just a setting of graphs where somehow you capture, instead of tensor rank, you capture the famous channel capacity. And the theory helps, studying that and many other settings. I want to, then the main theorem of this theory is the duality theorem. So I want to explain the duality theorem and what are these asymptotic spectra. And that's related to real algebraic geometry. It generalizes the linear programming duality, and it's related in several ways to positive Stahlensatz for polynomial systems. Maybe I'll give you a hint why this is. I want to show that the power of the duality theorem. I'll tell you about the Schoenhagen-Tau theorem, which is very important for matrix multiplication, how it follows directly from this duality theorem. I want to talk about the structure of asymptotic spectra in general, why it's important, and why you want to understand it. And I want to get to, we'll see if I get there, to Strassen's convexity theorem for the spectrum of matrix multiplication or connectivity of that spectrum. Maybe talk about, we extended it to tensor networks, so maybe I'll talk about them, but I have no particular plan of reaching the end. You can stop me with any questions. I want you to understand what's going on, what's the game, who's against who. So motivation, it's basically about just asymptotics in general and amortization. And you can think about, it's really hard to talk with this thing, when to breathe. To think about a general set, some universe. You can think of it as some maybe task, maybe computational. It can be, some combinatorial objects like graphs. It can be, economic things like, items you want to sell or buy. So there are motivations from all sorts of worlds, and some function, let's say to the natural numbers, which tells you the cost or the complexity. Well, it depends. Maybe for computational tasks, it's a complexity, circuit complexity of a problem. Here, it may be some parameter, the click number or the matching size of a graph. It can be the cost of something you buy or sell. Some function that we are trying to understand. So it can be cost or parameter, etc. And often this is difficult. So F may be difficult to understand. And one relaxation you can do when you are trying to understand this function is to think about amortized complexity. You say, what's the cost of having to compute or to perform many times the same task? Okay, so you can think of it additively or multiplicatively. So maybe if S is in this universe, you want to understand f of s, but you may want to understand maybe f of n times s. So performing this task n times, maybe it will be the limit. So in general, so n times s, and where is that? Maybe you want to understand some asymptotics, like how does it behave if we want to amortize it. So f of s may be the limit of n goes to infinity, the cost of ns divided by n. The limit should exist because this will be subadditive. So you can think of it multiplicatively, which is will be more convenient for us. You can do either just by exponentiating or taking logarithms of f. For us, we will actually prefer to look at the limit of f of s to the n 1 over n. So you can think of s to the n also as n copies, performing n copies of n. It's just written multiplicatively, and then you normalize by taking the root. And this is sometimes easier to understand, and it's a relaxation, so sometimes it is easier and may have better properties and may be as interesting, or in fact, comparing f, the relationship here is really interesting. That's what's being often called the economy of scale. So can you save if you, on average, if you perform the same task many times? So you want to understand, so the case that f tilde is much, much smaller than f, this is called the case where we have economy of scale. And there are many examples in fact, the Shannon capacity, which I'll not define, but a famous result of Noga alone answering negatively a conjecture of Shannon is that the Shannon capacity, you can achieve economy of scale. And appropriately defined. Also, one of the most famous examples where you can do a task many times in computational complexity is just computing matrix vector products. For fixed random matrix vector products will take n by n, will take n squared operations. But if you have n vectors to do it on, then you can run the matrix multiplication algorithm, and per vector you do much better. So matrix vector computation. On the other hand, there are situations where f tilde will be actually quite similar to f. And that's a case where we say we have a direct product or direct sum theorem. There are many examples here. If you define appropriately tensor products of LPs or SDPs, then the value actually multiplies. So LPs, SDPs. There are famous examples in computational complexity coming from hardness amplifications. I mean, you may know or not know some of these, and I'm just listing some, like Sohr lemmas, the parallel repetition theorem of Ran-Raz in two-player games, very important PCP theory. Information complexity for communication complexity. And others. Of course, you saw expressions of this form also in Cole's talk, those who are here. So it's very natural, and we are going to study a particular type of family of universes for which we can say something general about, Strassen's theory. So let me talk about, again, you can stop me anytime with questions, right? Let me talk about matrix multiplication. So yeah, we want to compute the product of two matrices, let's say, and B, they are n by n. And this is a bilinear function, right? So this yes, matrix multiplication and apply to A and B gives you AB, and squared inputs and 2 square inputs and square outputs. What's the complexity of this? Well, it turns out that it's not hard to see that what we care about is the multiplicative complexity. How many product gates do we need in an arithmetic circuit to evaluate this? It turns out that it's easy to see that additive complexity doesn't matter. It will always be at most a multiplicative one. So this really asymptotically is what governs the behavior. And of course, everybody knows Strassen's famous theorem that in 1969 proved that this multiplicative complexity, maybe I'll give it a name. Okay, before I state it, let me relate it to tensor rank, and then I'll state it already as a result on tensor rank. Any bilinear function like this is a tensor. For example, this matrix multiplication tensor will be a tensor of size n squared by n squared by n squared. So in general, when I talk about tensors, let's say this will be an element of f to the in tensor several times in this workshop. So it's just I'm looking here just at three-dimensional tensors, but it will be interesting just for reference to think about matrices also. And we can, everything I'll say generalizes to higher dimensional tensors, but I'll focus on three. And it turns out that matrix multiplication can be represented as a tensor. It is actually, so the tensor matrix multiplication n lives in n squared. It's true for every field. Everything I'll say is true for every field. So the theory will work for any field. How is it defined? You've seen it defined. This particular tensor, and will be basically in position. So there are n squared entries in each dimension. So if you are looking at the entry ij, jk, ki, then this tensor will be 1, and otherwise it will be 0. So it's a Boolean tensor, and it's filled with its entries. So a tensor is a trilinear function, or it's a table, a three-dimensional table. And matrix multiplication is this particular Boolean tensor. And it turns out that the multiplicative complexity of such an algorithm is exactly the tensor rank. So what is the tensor rank? What's the rank of a tensor in general? A tensor like this. The rank of a tensor is the minimum number R such that T can be written as a sum R of, UI. Of rank 1 tensors. So these are rank 1 tensors. In the case of matrices, there will be just two of them. That's rank 1 matrices, and it's the same definition. So what we are interested in this matrix multiplication, we can upper bound it by giving rank upper bound on its tensor. And what Strassen did in '69, his famous result, sort of somewhat shaking the algorithmic world, is that rank of the matrix multiplication tensor on two elements is at most 7. 8 would be the obvious thing, or n cube is the obvious solution for matrix multiplication, but he managed to do it with 7. And of course, immediately, and this is an important fact, matrix multiplication is a problem for which you can apply recursion. So this immediately implies that the tensor rank, the multiplicative complexity of mmn for any n is at most n to the log base 2 of 7. Why is this? Because how would you compute? Would you multiply matrices of some large size n? Just divide them, so everybody has seen it, to 2 by 2 matrices of blocks of size n over 2, and you'll apply this algorithm at the top level and recurse. Right? That immediately gives this result. But seeing this result actually means that, of course, he could have proved if there was a different upper bound here, if we could, for example, could prove that for some number k is at most R, this will imply by the same recursion, we'll just divide it to k by k blocks. This will mean that the rank of matrix multiplication n would be at most n to the log base k of R, right? So there is an exponent that governs the growth of these numbers. And where does it come from? It comes from an asymptotic version. As you see, I mean, we could have picked any k here. So what we should really look at is not the rank of 2 by 2 matrix multiplication, but actually on the limit of what the tensor power, I mean, think of k as the power of 2. How it behaves in the limit as we take higher and higher powers. So what we are really interested in is what I would call the asymptotic rank, which is exactly an object written down here of any tensor T, like the tensor of matrix multiplication of 2 by 2 matrices, or any tensor, would be the limit, as let's say m goes to infinity, of the rank of the tensor power of Tm times 1 over m. Okay, so everybody's happy with this definition. So you take tensor power of a tensor is just like the tensor power of a matrix, right? Tensor power of a matrix is still a matrix. So, and the tensor power of three-dimensional tensor is still three-dimensional power, a tensor, much larger space. So these things will turn from A to the M, B to the M, and so on. Okay, so we are interested in this. So here you see a setting where the asymptotic complexity is the complexity you want to look at. It's not just the relaxation. If you want to study algorithms for matrix multiplication, you really want to understand the asymptotic rank of the matrix multiplication tensor. In fact, if you prove any upper bound, so Strassen happened to prove an upper bound on the rank, but if he proved it on the asymptotic rank, the same result would follow, right? And the famous, omega parameter. Omega is the infimum that one n, you can write it n to the omega, but this is the same as writing that the rank mm2, because you can go to tensor powers. Of course, you will only be dealing with tensors with matrix multiplications whose sizes are powers of 2, but up to constant it doesn't matter. Yes.
So can this asymptotic rank depend on the field?
Yes, of course it can depend on field.
It can change a lot.
Yeah, it can change a lot, and but the whole theory does not depend on field. Yeah. Okay. So, any other questions? So, we see that we are interested in the tensor rank. This is, of course, I didn't mention it. Tensor rank has zillions of applications. You can start mentioning them: statistics, machine learning, quantum gravity, in fact, general relativity, wherever you want. Understanding the rank is important for many reasons, and we are focusing here on understanding rank of matrix multiplication. But in this context, we'll see that looking at tensors in general is valuable, even if we want to understand just the tensor rank of matrix multiplication. So good. So I introduced this asymptotic rank of matrix multiplication. It's motivated by the fact that it's really the true complexity, it governs the true complexity of matrix multiplication, and it motivates the following. Let me just look at rank in a slightly different way, and this is where symmetry will be clear. Erase is better. Oh, no, it's just a black, it doesn't. Should have learned from previous talks. Maybe I'll use blue. Yeah.
So over complex number, is this for this particular tensor, is this known to be robust in some way to performing the tensor?
I think it is, but yeah, I'm not. I'm not absolutely sure. Maybe there are really tensors with a small tensor rank, and you perturb them randomly, and the randomness causes. Yeah, I'm not sure. For every fixed tensor in this field, focus on the tensor. So we have this asymptotic complexity, and it motivates an asymptotic order of tensors. But before that, let's see how to interpret this definition of rank. One way of saying it is that, I want to motivate this. The rank of T, I want to say that it's at most R. So I wrote it in one expression, but I want to write it in another. If T is less than the identity tensor, which is R by R by R, but just a diagonal tensor, the tensor which has one of them, the diagonal, I guess, 0, 0, S1. And what do I mean by this reduction? And this is where the symmetries come in. I mean, the tensor rank would not change if I do a linear transformation on any of the sides. Like if I do a linear transformation here, some matrix A applied to this space, I do some matrix B to this space, and matrix C applies to this space. Actually, even going to F to the A prime, B to the F to the B prime, F to the C prime, I just change basis or just reduce in any way So I take arbitrary matrices and I can transform the identity matrix. So this means that there exist matrices A, B, C, where when I apply A, B, C to the identity tensor of size R, I get T. This is the same for matrices as pre and post multiplying by other matrices. You can only reduce the rank. So that's the order that we get on tensors here. So here I compare tensors T to particular tensors, but in general, you can say that T1 is at most T2 if and only if there are such matrices such that T1 this is a partial order on the set of all tensors. I'm considering tensors of all sizes, and this is a partial order of tensors, which in the case that the right-hand side is the identity tensor, tells you the tensor rank. Okay? And given the fact that we were interested in asymptotic ordering, so if we take such limits, it means that we have an upper bound plus little epsilon on the right-hand side, we might as well define, and that's a key definition. So this is a partial order that's given to us. So that's a natural partial order. Here we have the partial order or pre-order. And now we have the asymptotic partial order, which is supposed to capture the asymptotic rank. And it will be the following. It's very natural. So we say that T1 asymptotically is less than T2 if, if for some large n, basically for all large n, we have, when we limit, we take n copies of this tensor, we can reduce T prime to it, or T1, T2. We can reduce it, and here we allow n plus little o n. Allow a little more. So in the limit, it will disappear. Okay, so this is an asymptotic partial order. And this is a relaxation of this partial order. And it's much more, amenable to analysis. It's much more accessible, and we'll see soon how. So first, I want to make sure that everybody is, is clear about,
But there, they don't have the same dimension, right?
You don't. Your dimension can change. This A, B, and C are not square, are not invertible. They, like you apply to a matrix, apply pre and post multiply by any matrices A and B, you get a smaller matrix, and the rank of this result is at most the rank of that. So in the same sense, you have just 3 of them.
Okay.
Yeah. Okay, so we have this asymptotic order, and this is what we are trying to understand. So in order to understand this, we need to observe 2 more. So our universe, I already erased this. S, the universe we are playing with, is a universe of all tensors, 3-dimensional tensors of all sizes. We have a partial order of it, but we have also a ring structure on it that we are going to use. So adding and multiplying tensors, in fact, multiplying we just saw. So S is a set of tensors. We saw a partial order on them. And we also have T1. Well, let me start from products. What is a multiplication? Multiplication is T1 tensor T2. Okay, so that's it's a commutative operation on the space of tensors. And addition is T1 T2, by which I mean just putting 2 tensors, below each other. Just like doing with matrices, putting them as block diagonals on a bigger matrix. So that's how you add tensors. That's another operation. So tensors are also semi-ring, semi-ring. This set, and there's a partial order. In fact, the partial order is compatible with these operations. If you, if you add two smaller tensors and you add two bigger tensors, you'll get a bigger result and so on. And same with multiplication. So we have this additional property, and the final property that I want, and this is a setting in which the Strassen theory will apply, is the existence of the natural numbers in this semi-ring. Right? This is like the number, the integer R. Right? So in the semi-ring, so S has inside it the integers. This is a set of R for R. So they are the ones that we know this is the total order on the integers. We know it, and it somehow allows us to scale or to bound the ranks of all other tensors. That's what we are seeking, the rank or the asymptotic rank of other tensors. So we saw that the universe of tensors is a semi-ring. It has a partial order, and the natural numbers live in it. And in fact, Strassen considered, even though he is really interested in tensors and matrix multiplication, he's considering all such semi-rings. So let's see how I'm doing. Okay. This will probably take another 5 minutes. So now I want to tell you the duality theorem. So I want to say what we are interested in and the rank in any ordered semi-ring, any pre-ordered semi-ring. Okay, so we have in general S is what this kind of property is sometimes called the Strassen semi-ring, pre-ordered semi-ring. So we have any partially ordered semi-ring with the integers inside it, and we want to, I give you an element S, and I want to compute the minimum real number R, such that the rank of S is most R. Right? This is finding this is an optimization problem. What are the constraints on this optimization problem? It's a bunch of inequalities. What are the inequalities? These are just all inequalities that exist in this infinitely many, maybe uncountably many things of the form AI. All the relations in this partial order. Anyway, it's some, I don't know, space. And in this space, we'll soon make it more concrete, but it's a space. In this space, constrained by these inequalities, of course, there are relationships between this, given element and, the elements BI and AI. Maybe it's a sum of tensor products of the others or something, right? Or maybe there are many ways of writing it like that. In particular, you can write it as a tensor, given its tensor rank, you write it as a sum of rank 1 tensors. So there are all these inequalities, and you want to solve this minimization problem. And Strassen's main theorem is the duality theorem. It tells you that this optimum is equals to the maximization of something else. Okay. will be the maximum of some function. And this function will be, I'll tell you its properties, but it will be a function from the summary to the non-negative reals. Okay, so it should look familiar. It should look to you familiar from other duality theorems that you see. You have a minimization problem, you write the dual, and the dual will be a maximization problem with new set of variables. What will be the variables? These are the variables that associate to every element in S some real number. And what kind of properties, what is the set of fees that we allow? Well, how do you get information from this set of inequalities in general? I mean, in our programming or in other polynomial real algebraic geometry, well, you can certainly, this summary, right? You can add inequalities, you can multiply inequalities, and you send these to real values. If you do it in a monotone way, preserving the order, you can also use it. So that's what you want. So you maximize this overall phi of this type, which phi of A. So exactly what you think? They are additive. Multiplicative. Well, you want to normalize, you want the integers not to disappear by some mechanism. So phi of 1 is 1, so it's normalized, which means that phi of n is n. And monotone. Phi is monotone under the partial order. So A is the smallest b means that phi of A must phi of b. So put some natural conditions. In fact, using these natural conditions, weak duality is not hard to prove. This maximum is at most that minimum. It always lower bounds it. And the main thing is the converse, so there's strong duality. So that's the main duality theorem. So first, I want to make sure that everybody understands the statement of this duality theorem. There's in this very general abstract setting, you can still characterize the optimum of this type of optimization problems by this dual formulation.
This minimum is less or equal than value of f at NES?
Yes, yes. So in particular,
and taking like
yes, so in particular, so let me write it down what Jan said. So in particular, the rank of S for any S is the maximum over all phi. So let me call it, so this set, this kind of set of functionals is called X of S, and this is the asymptotic spectrum. Only one S. Asymptotic spectrum of S, so this family, and this will be the max over phi of S. This is true for every S. And more generally, for any 2AB in S, A is less than or equal in the asymptotic order than B, if and only for every phi in the asymptotic spectrum. A B, these are three numbers. Right, so you characterize this explicitly this asymptotic order if you look at the, you really care about asymptotic. There's no such characterization for the rest. Okay, so this is the duality theorem. I want to make sure this I can state, and I want to, oh good. So again, questions about just a statement of the duality.
Is it important that you use integer there?
Yes, it's a very good question. And in fact, I didn't, and I'm not going to say almost anything about the proof of this theorem. But one way, I mean, we give a somewhat different proof than Strasson's proof. He appeals to some duality theorem of Dubois and Cadison on rings, but you can do it really explicitly and give the full proof without appealing to anything. And in particular, you relax these two rationals. One relaxation is two rationals. Basically, if you think, well, in fact, it's not clear that this is not an empty set, right? It's not clear. If you think a little bit, you'll find that it's not an empty set because, for example, if you flatten your tensor to a matrix in any way, right? Let's say one of the three against the other two, and you look at the rank of this matrix for every tensor, you can define it. This will be a ring homomorphism. It will be additive, multiplicative, because that's properties of matrix rank. So this is non-empty, but that's sort of like a trivial element of the spectrum. Okay, but so now you wonder what can you do with this? Okay, so first of all, what is the structure of this asymptotic spectrum? You can at least understand it in some cases, and in particular in cases that will be of interest, if the ring is generated by a constant number of elements. For example, if you are interested in the matrix multiplication exponent, you can restrict yourself to the semi-ring generated by matrix multiplication, just adding it and tensor product with itself. That's also a semi-ring, and it has all the properties there. So if S is generated by some finite number of elements, then this asymptotic spectrum is really a set in R to the K, right? Because I claim that these are ring homomorphisms, so they are, basically polynomials. If you want to understand the value of polynomial, if you know it, in a ring like this, if you know it is the generators, you can just compute it in anything else. So here X is really will be the set of, it can be identified with a set of phi of A1. This tuples phi of AK, all these phis. So it looks like a recursive definition, but I hope you understand what I mean. It's sufficient to just describe it at the generators, and then you know it for all other values, because any other element of the semi-ring is a polynomial in this element. So this is a subset of R plus to the K, so at least you can think about it. This may be infinite dimensional. And a priori, you can ask what is this, you can say that it's very easy to see because we have polynomials, this is a closed set. But what else can you say? Well, in general, there is nothing you can say. For any closed set in the R to the K, I can describe for you a ring which will have this as its spectrum. So there is no information there. So the question is, what information do you gain in tensors, in the matrix multiplication semi-ring? What else do you know? And let's see one thing we can know, we can infer from this. It's extremely important, powerful for matrix multiplication algorithms. Okay, that follows from duality. Let's see if my theory is correct, that erasing blue is easier than erasing black. Yes, amazing. So I'm here at the Tau theorem. So yeah, I didn't say it, but if you think about this case, the finite generated case, you can now think of these inequalities actually as polynomial inequalities. So you are in the real algebraic geometry setting, you are minimizing some polynomial expression subject to some polynomial constraints, abstract polynomial constraints, and you translate it to a dual, which there are papers of Fritz and some others actually in the last 5 years or so, which actually, so it should remind you of the positive Stahlensatz case and the duality theorem for real algebraic geometry. There are several such statements like this, and he connects these type of results to Strasson's duality theorem. One, they are incomparable, but there are relationship between them. If you remove one of the operations here, either you're left with only additions or only multiplications, then you get a semi-group, and then you can check that this duality theorem generalizes just linear programming. That's what happens in, let's say you look just at addition, you'll see that you get something that generalizes linear programming. And in a finitely generated case, it is linear programming, duality. So it's a connection to optimization in real algebraic geometry. So I want to tell you, maybe this is the last thing I'll have time to tell you, is how to apply to matrix multiplication algorithm. So I want to tell you about Schoenhager's tau theorem. And I don't know how many people have heard about this, but one way to introduce, and why tau? Tau is because of omega. You remember omega is the exponent of matrix multiplication. Tau is another Greek letter. Somehow Greek letters are really popular today for bad reasons. So here's a trivial example of the tau theorem. Here's an example. If I prove that the rank of the matrix multiplication tensor, or it may be for some n, is at most n to the tau, so I have an algorithm, right? If I prove this, then this says that omega is at most tau, right? It's a triviality, right? I have an algorithm, maybe there's a better one, but it's at least one algorithm. Okay, so this is what Schoenhager is asking. Well, suppose that I have another algorithm. It's not for matrix multiplication, but it's for the direct sum of two matrix multiplications. You have to multiply n1 by n1 matrices, and then you have to multiply n2 by n2 matrices on a completely disjoint set of variables. Maybe you have an algorithm for this that's fast. So suppose you discover rank or even asymptotic rank of n1 and 2. Suppose you discover that, let me call it, well, R, which can be expressed in a form like this, let's say n1 to the tau plus n2 to the tau. Does this imply that omega is less than tau? Are such algorithms useful to bound the matrix multiplication exponent? So you remember here, Strassen used, Strassen proved that rank of MM2 is at most 7, and this immediately, so 7 is 2 to the power log 2 of 7, and this implied that omega was less than something like 2.8, much less than 3, right? That was Strassen's result. Turns out that Schoenhager did the same. He found a clever algorithm for something like this. Actually, it was more complicated. I'm not going into rectite. There was actually an upper bound for rectangular matrix multiplication, but doesn't matter. It's the same principle. He found an inequality like this and used it, and the theorem that this actually happened, to derive in Schoenhager's results, an application to this kind of method. He used something like this to prove that omega, so he proved some rank bound like this, and he got omega is at most 2.55. So see, such inequalities are useful. So you have to cross out this. So what he proved is what's called the asymptotic sum inequality, and he says that if you can prove any upper bound like this, okay, and sub k and sub I is at most sum of n sub I to the tau, this implies omega. So that's a theorem. That's the theorem. That's the tau theorem. Asymptotic sum inequality. And if you think about it, what it really means is that there's no way to save that this direct sum problem. There's no way to save on it. So this is equivalent to saying that this asymptotic rank of the direct sum of MM and I is the same, actually. It's, it's even the tighter bound that Strassen, I said Strassen proved, is the sum of the asymptotic ranks. Okay, so it's another scenario. We talked about direct sum in the beginning. When here you have no economy of scale. And because you have no economy of scale, then a bound like this gives you a bound on omega, on the exponent of matrix multiplication. Okay, so that's a theorem. Let me tell you about the proof of this theorem, and I think that maybe the most I can do. The proof is really simple when you have duality. I mean, it's sort of amazingly simple. So what is this expression? Think that the ni's are 2 to the ai are just powers of 2, right? So this means that each one of them is a tensor power, some ki ai tensor power of mm2. So it's a polynomial in this single generator mm2. Okay, so if our ring is generated by one element, then you should think of these elements for this purpose of as being the matrix multiplication of 2 by 2 matrices. Such a sum is a sum of powers, so it's just a polynomial in this this element. I claim that for any phi in our spectrum, in the spectrum of S, phi, and for every polynomial, let's say with integer coefficients, it doesn't really matter. Let's think of it as a variable here. So everybody's happy with this. I mean, phi is a ring homomorphism. It adds on additions and multiplies on multiplication. So this is a trivial thing. But now let's see what is the, and this is a particular polynomial, right? This is a particular polynomial. So what do we do? We want the rank, the asymptotic rank of P of A, this sum. By duality, this is the maximum overall phi in the asymptotic spectrum of P of, right? And now you can move the phi inside and the maximum inside by monotonicity. And this comes to be P of maximum P of A. And you get the right-hand side. This is it. It's amazingly powerful. Okay, so that's one application. There are other applications. I will not talk about them, but since I have just a couple of minutes, let me tell you what I didn't tell you about. It turns out that it's really nice that you can infer something from inequalities like this. But what do you do if you have the rank of some direct sum of matrix multiplication tensor is at most the sum of some other matrix multiplication tensor? Here we have an integer. Suppose you have here another direct sum. Then this inequality is just relating two polynomials, not relating polynomial to a real number. So you cannot use monotonicity. What do you do? Well, it turns out that I would have pictures, but let me not get into this. Let me just say that if you want to derive algorithms from inequalities of rank of one direct sum and the rank of another direct sum, then you cannot hope for anything if you don't know more about the spectrum. Now, what do we know about the asymptotic spectrum of matrix multiplication? We don't know much. But we know this much. The asymptotic spectrum of matrix multiplication, which might as well be this. You know that subset of the reals, it's one-dimensional. And so here are the reals. And we know that 4, 2 to the 2 is in there. And we know also that 2 to the omega is there, because that's the maximum it can be. And we don't know anything in the else. So it turns out that this upper bound means that, you know, basically if we have a polynomial that, so the spectrum lives here, it's a closed set, maybe it's a union of intervals. Here we have R minus P of, R minus P of X given by this is non-negative on this spectrum. And if it cuts here at a point R, we get an upper bound on the matrix multiplication exponent. But if we have an inequality of the type I was talking about, you know, between two, you know, maybe we would have something that looks like this. You know, something that may look like this, which is also positive on the spectrum, but it, you know, how do we know? How do we bound this maximum? Well, there will be one easy way. If this spectrum was connected, so we knew another more information about the spectrum. If we knew it was connected, it was one interval, then we would. This cannot happen. I mean, it would have to look something like, I don't know, maybe it would look like this. But since we know point here, we would know an upper bound. So anyway, the upshot is that the last theorem I want to state that the matrix multiplication, the spectrum of the matrix multiplication is connected. So you can infer more. He proves something else. He proves it for, you know, rectangular matrix multiplication. We generalize it to all tensor networks. This kind of connectivity in fact star convexity of the spectrum in higher dimensions. But I guess I have no time to tell you anything about you know, the proof unless you ask me some questions. And yeah, I guess I almost covered almost what I wanted to talk about. So let me end here. Questions?
Very much. Any questions?
So, all right. Do I need to do?
All the Zoom people.
We'll be even louder.
Okay, good. So if I properly understand, like the computational model that potentially one can look for faster multiplication algorithm, doing checking some real inequality, some optimization, like real numbers optimization.
Yes. Yes.
And the current one, they're completely discrete.
They're all discrete. They're over, you know, they'll be over real space like real algebra.
No. When people now looking for the like faster, all this like discrete. So you compare that some dimension with another dimensions.
Yes, they do more things. They do that even storage. They don't just use, although this is used sort of routinely. There are things about computing partial matrix multiplication with laser methods. But yeah, they basically prove inequalities of this type and infer from them, you know, bounds on the exponent. Yeah.
Any other questions? Any other questions?
So this proof that you are showing, right? So you're saying you take an algorithm for some multiplication, then this gives a bound for omega on omega, which then is again
is an algorithm.
Yeah, is an
yes,
algorithm.
Absolutely.
So this passage from an algorithm to an algorithm is somewhat explicit.
Yes,
So you can.
yes, it's explicit in the sense that you can translate it to, all this is using the asymptotic. So what, these are asymptotic inequalities, right? So what you will do is you say there's some finite size which approximates the bound you got here by maybe an epsilon, and you get a bound that omega is equal to tau plus epsilon for any epsilon you want. Yeah, and this will be an explicit algorithm, probably expensive because the numbers will be large, but yeah, theoretically that's how you get that. It's explicit. Yeah.
So you get like a super constant in front, which you don't care about. So it's C epsilon.
It's not
times-
the constant is one problem, and the other thing is that there's an extra epsilon in the exponent. Yes. Yes. So it's basically for understanding, is the complexity of matrix multiplication quadratic, or quadratic will mean 2 to the, n to the 2 plus epsilon for any epsilon. That type of result, of course, it will not mean that we can have a real software that does it in this. Yeah, fine.
Any other questions?
Thanks for the talk. Do you have any sense of whether the things in the asymptotic spectrum look like, like I guess you have as Matthias was talking about, you have like the ranks of the kind of flattenings. Those are somehow at least you could write them down as like, as in using determinants of matrices with entries depending on the tensor. Should it
There will be points in the spectrum. They will come for flattening of the tensor.
Yeah.
And then they have what he described is that these are not, this is just a finite set, in fact, 3.
Yeah.
What he described is that you can actually get an infinite number of points in the spectrum of matrix multiplication, of rectangular matrix multiplication, that's a 3-dimensional space, using these, linear combinations of entropies. Yes, so there are continuously many other points in the spectrum which they are, describing this way. We don't know whether they are everything. We don't know whether the set is convex. What Strassen proved is that it's star convex. And so when you, of course, in the one-dimensional case, if you just look at square matrix multiplication, connectivity, convexity is all the same stuff. Yeah.
Could you prove that they were at least like that the function has like some expression? Like, are they going to be polynomials? Maybe like polynomials and logs and stuff like that, or
No. I mean, you should think about the fact that there's no obvious way to generate any other point except 4 and 2 to the omega for just square matrix multiplication. It's something that would be, a ring homomorphism that's monotone on this, semi-ring is generated by one element. It's non-trivial. It's very hard to know anything, and this proof is extremely indirect. You have to go to rectangular ones, and then you have to do some magic, which we have an interpretation of the paper as actually as an error correction of faulty matrix multiplication algorithms. I mean, he doesn't describe it like this, but I mean, the essence of this is a compression result which shows that in every erroneous in a particular way, low-dimensional errors in any given matrix multiplication algorithm set for n by n matrices hides a perfect n over 2 by n over 2 matrix multiplication algorithm. And that's, in a very clever way using the asymptotics, this gives this connectivity result. Yeah, so lots of details you can find out in the survey that I think is, we're happy to get comments for anyone.
The asymptotic rank for this case, is it decidable? The computation.
I think this was studied. I'm trying to remember. Okay, so another example I mentioned is Shannon capacity.
Yeah.
It turns out to be a maximization problem, so it's sort of it's a subrank, but it doesn't matter. There it's undecidable. So a parameter like this in the context of graphs is undecidable. I'm not sure about the.
Yeah, that's why I'm asking.
Yeah, I don't know. But in some cases of natural like that, it's undecidable.
So
one question is that, so you're saying, oh, if we're trying to find a point between 4 and 2 to the omega, but if they're equal, is there any other kind of?
No, if they are equal, then this is one point.
Yeah, exactly. Then you won't be able
In
to find
fact,
it.
think about the case d equals 2 of matrices.
Right.
For matrices, there's only one point. It's the rank. The rank is the only ring homomorphism of matrices to the non-negative real, that is multiplicative, additive. So there the spectrum is a single point. Here the spectrum is continuous, unless it's one point.
Unless it's right. And then is there any other like kind of could be like conjectures that you could expect as well that don't involve the asymptotic spectrum, that maybe there's other implications that say, oh, if the spectrum is one point, then such and such would happen?
If it's one point, then you understand everything perfectly. So it's you know, it's sort of, I don't know, a trivial case in the sense of this asymptotic theory. But we don't, you know, in general, more interesting examples, we think it's probably not a single point.
Yeah. Oh, yeah. Sorry. Then the question would be like, if it's not a single point, is there any other kind of, you know, easier conjective statement that would be implied that at least you can try to verify or not verify? Like, is there?
Yeah. So as I said, if you know that it's not only not a single point, but it's you know, connected, then you can show that certain inequalities will imply a bound. If you know that the set is convex, you will have even stronger implications. You can have even more general inequalities implying a bound on omega and so on. So in some settings, in the setting of graphs, which relate to the Shannon capacity, then you know that it's actually convex with the result of Peter Werner. So in some cases, it's known that it's convex. In the case of rectangular matrix multiplication, it's not known. Star convex is known.
When you get circuit lower bounds or something, if it's omega, because you get like
Yeah, of course. I mean, I should have said that the only reason I'm in this game is because of arithmetic complexity. That's for me is the motivation. And tensor rank lower bounds are arithmetic complexity lower bounds. It's a lower bound for particular circuits, bilinear circuit, for bilinear function, counting the number of multiplications. We don't know a single, like, we don't know anything in terms of complexity. That's a summary of our knowledge. More specifically, we don't know any explicit example of a function. Let's say a bilinear function requiring more than, you know, the size of the input many multiplication up to a constant. We just don't know that. The matrix multiplication is just one explicit example. We don't know any tensor for which the tensor rank is bigger than the, you know, the size of the tensor. And we are looking for methods of proving such lower bound.
Any other questions from online? Anyone on Zoom? Okay. Well, thank you very much again.